Okay, welcome back. This afternoon we'll be talking mainly about sensing. The topic of my talk today is non-destructive quality measurements and their practical applications. I'll be talking a little bit more about the theory because then we've invited two different companies that will talk about their application. And Mitch is going to talk a little bit about a topic a tad different that we're trying to explore as an alternative measurement technique for quality of produce. So again, my name is Irwin Donis-González. I am an extension person and post-harvest engineer in the Department of Biological and Agricultural Engineering. As part of this panel, we have Mitchell McCartney. He's the Director of Research for the Biomems Lab at UC Davis. Mitch will be talking to us on the topic of VOCs. We then have Galen George. He's a certified food scientist, alumni of Michigan State too, like myself. I just learned that yesterday when I was reading his bio. So go green, George. He's from CID Bioscience. He'll be talking a topic related to portable sensing quality equipment. And last but not least, we have Roberto Moreno from Tomra Sorting Solutions, who will be discussing inline sorting applications. So I like to start my talks all the time when I talking about quality, and I ask, and I want to see some hands here right now. Of everybody here, would you eat this product? Yes or no? Yes, hands up. All of them. Would you eat that avocado? Would you eat that pineapple? That's a tart cherry. So yeah, it is. You caught it. You probably wouldn't eat that one, huh? Because it's tart. But other than that, yeah. So apparently you could tell that the avocado was defective in the inside, but just looking at the surface? No. I saw that there was something. I see. Well, you must have X-ray vision then. The take-home message of this slide is that we can talk about quality, but we need to find a distinction, especially in produce, between external and internal quality. And what we have found is that they typically do not relate. And it's tough to measure, especially internal quality, with the available techniques that we have. And that is one reason why I felt the liberty of inviting Mitch, because hopefully other alternative techniques can allow us to more accurately measure internal quality attributes of product. As we can see here, this is pictures that I have taken, by the way. This is no lie. This is water core and apples right here in the corner. We have some physiological deficiency here in avocado. Every time that I'm giving this talk, Mary Lou Arpaia reminds me of what it is, but apparently it's mismanagement of temperature and during maturity. We have translucency in pineapples. It's a big problem, especially when you do not manage irrigation properly. This is a big issue for many companies, actually. And I used to work with both Del Monte and Dole in trying to solve and better measure internal translucency. It's a defect of pineapples. And last but not least, we have here tart cherries with an insect, which we can't even tell from the outside that this is what's inside. But before we continue, I would like to define what is quality. Quality is very subjective, basically. And it's just defined as a unique attribute or feature possessed by a product, in this case, a fresh commodity, that defines its degree of excellence or superiority. That doesn't tell us anything, huh? I mean, but we can define excellence, we can define superiority. And in many instances, especially with the fruit industry, the word quality is used in various ways. And it's in reference to market quality, edible, shipping, table, nutritional, internal, and appearance quality. And this also includes flavor and so on. As you can remember, as part of the keynote speech that we had with Gabe and Walt, I asked the question to Angela, what was her major concern? And she said flavor. And that is a major concern for many. And that is another topic that we need to talk with Mitch regarding how can we use volatiles, for example, to determine the flavor or infer the flavor and aromas. But that's not the topic of my talk. Basically, also quality is defined depending in which segment of the production you are. In terms of producers, a producer wants to have a product that has good appearance, a few visual defects, but at the same time that it's a high yielder, that it's disease resistant, easy to harvest, and it's concerned about its shipping and harvesting quality. The distributors, on the other hand, when you go to any Nugget or Walmart or whatever, they're just basically concerned about less. You know, they want good appearance, they want it to be firm, and they want it to store well. But from the consumer side, as we learned from our keynote speakers, it goes beyond that. We look at the appearance, firmness, good flavor, aromas, and nutritional value. And although consumers buy on the basis of appearance and feel, their satisfaction and repeat purchase are dependent on the good edible quality, flavor, and aroma. A perfect example, at least at a personal level, for me is mangoes. It doesn't matter how beautiful the mangoes look here in the US, I stopped buying mangoes because their appearance, they look great, but they do not taste as well, especially when you come from the tropics. So I do not buy mangoes, so I don't have any repeated. So how can we change that? And that's part of what we will be discussing today. By far, when you go into any produce section, what defines you purchasing a piece of product is its color or its an external appearance. So we've invested a significant amount of time in trying to ensure that that appearance is in part to the consumer's quality standards. And visual appearance of a product can also be not only an indicator of quality, but also a maturity indicator, chlorophyll levels, pigments that can indicate maturity and ripeness. And in many instances, this color is also related to flavor. I say in many instances, but not in the majority of cases. We assume that that the soluble solids or the sweetness of a green mango is less than something that is nice and colorful and yellow or green. That's our assumption. But in many instances, this is not the case. And in other cases, we can also, due to changes in color, as we could tell here, we can tell if the product has any sort of defect, indication of degradation, and so on. So how do we measure color? It's easy to measure length. We have rulers. Mass too, we have balances. But color is not as trivial. And how do we ask a computer to relate to what we see as humans as colors? So a perfect example here is, what color is this apple? What color would you say this apple is? Red. Just red? Any other? There you go. So now that's the subjective measurement of quality. We have red, burning red, crimson, bright red, whatever. There's many definitions. And depending on who we are, we can discern color differently. More specifically, yesterday it was mentioned that in the majority of cases, in the packaging line, you see that women are the ones that are packaging or the end packagers. And this is for a specific reason. Women are much more versed at differentiating color than men. Actually, there's around 10% of the female population in the world that has 4 cones and not the typical 3 cones that we have. And there's basically non-existent in the male population. Add another layer to that, around 15 to 20% estimate of the male population is colorblind too, because color blindness is associated to the Y chromosome. Okay, so because of that, now we know women are better at discerning color. and therefore the quality of produce in comparison to men. So let's start by understanding color. Color happens when we have these four components. Probably one of the most important is illumination. If we do not have illumination, if we're in a dark room, basically we can't see color that well. Second, we have the object. In this case, I'm using an apple as an example. We mentioned that we think it could be crimson, red, whatever. Third, we have a detection mechanism. Our eyes are typically what we're doing. And fourth, interpretation, or the invention of AI. We all talk about AI techniques and neural networks and so on, and there's no better AI than our brain. And we're making a lot of interpretations when we get a product, when we go to the store. We look at bruising, we're looking at changes in color, we're looking at the other attributes, so we're computing a lot. And now we're trying to force computers or try to train computers to do the same. It's not that trivial, it's very complex. And most importantly, all four components must be defined to know the color. And by define, I mean, even if there's a small change in the illumination, we will see a significant change in color. There was a question yesterday when they were talking about the robotic harvesters. What's the problem with illumination in the middle of the day compared with at night? It's a huge problem. If we do not control illumination properly, then those sorting or those algorithms or AI that is discerning color are not going to do anything for us. Doesn't matter what we do later. Doesn't matter if we have the fanciest camera. Doesn't matter if we have the fanciest AI. Color is going to be discerned differently. Let's talk a little bit more about the electromagnetic spectrum. Color, generally, when it comes from the sun, it includes every range of colors, okay? And beyond that, beyond to what we even see. Typically, as humans, and I say typically because it's not the case in the majority of instances, we can see color between 380 and 780 nanometers. We know that other animals like snakes, for example, they can look beyond that into the infrared range, so they can see heat or the emission of heat of bodies. So they're really not relying in color. They're relying on another spectrum of light, of that spectrum, to infer their environment or look at that object. The nice thing is that we have equipment now that is able to do that. In the medical industry, for example, we couldn't do without computer tomography. We couldn't do without x-rays. And that's simply a different wavelength. It's disregarding all of the component of color of this electromagnetic spectrum, and it's targeting a specific section where that wavelength, because of its increasing energy, can penetrate matter and allows us to look inside a product, for example. And I'll show some examples at the end. So let's talk a little bit about the physics of light. What happens when light from the sun hits a prism? It's typically separated into its components or into its color components. Light is a wave composed of different frequencies with different energy at different components. That's what we know as wavelengths. When white light is, and again, white light is a combination of all of these components within the visible spectrum. When light hits or strikes an object, pigments are not added. Pigments are already embedded within the fruit. But what's happening when color strikes this object? What happens is that rather than us observing what is the color of the pigment, we're actually observing selected frequencies that are reflected from that produce, in this case, this apple. Here, we can see that for us to have this kind of like yellowish orange apple, light that needs to be reflected is between the blue range for us to have a combination of all of these colors thereafter. So really, we're relying on the absorbed light to determine what color is, or how the electromagnetic spectrum interacts with the object and how much light is being reflected. So here we're absorbing the blue light and we're reflecting every other wavelength so that we could see color. While it is the reflected portion of the light that we see as color, it is the absorbed portion of the spectrum that controls the color. So for us to look at this cyan color, it actually means that there's red missing, or red is being reflected. And so on with the others, yellow and magenta, as we can see here. And the physics of light absorption allow us to better understand what is happening not only at the pigment level, but also other compounds that get excited that are not necessarily associated to color. Here, we rely on what's called the Beer-Lambert's law, where light emitted from the sun is going to be absorbed. It interacts with the tissue, in this case, the slice of fruit, and there's some light that is being transmitted. And the absorbance of that light is related, or light absorbance is related to a pigment concentration, in this case, chlorophyll. But there's other wavelengths of light, for example, in the near infrared region, that do not necessarily excite chlorophyll, which is a pigment, but it excites other compounds like sugars, lipids, proteins, whatever. And it's going to absorb or reflect light within specific regions. And that's how we can use optics or light to infer other properties, other constituents, sweetness, for example, if we can target those regions. And I'll talk a little bit specifically about those regions. Of course, there is other issues like sample dimension, light transmission, the type of light, and so on that we need to take into account. But generally speaking, what the take-home message of this is that the compounds within a slice of fruit are reflecting and absorbing wavelengths of light within the visible range, but also beyond. And that beyond is that we're interested, specifically, we're trying to explain additional quality attributes of the fruit. Changes in this too, both in this case, the pigment concentration or the sample, are going to define how much light is absorbed and transmitted, and thus give us a color, or thus give us a spectrum specifically for different levels of sugars, for example, if we're targeting that region. The human eye actually, we are around 33%, we're assessing around 33% of the whole color spectrum. So it's very small. We're very selective. Actually, these are the specific regions from our cones, from our eyes, that are inferring color. So it's very small regions within the spectrum. So we're not a hyperspectral imager, for example, where we're looking at every single wavelength. Through evolution, our eyes have developed into specific receptors within this range. This brings some issues, and this is one big issue that we experience in the field of sorting and imaging and so on. It's called metamerism. This is the phenomenon where two objects with different reflectance spectra appear to be the same color. As soon as we change the light, then we see that there's a difference. The perfect example here is these two buddies right here are outside in the sun, and they think that their bags are the same color, but as soon as they go into a room and they have a different color source, whoa, now they're different. Why is that happening? Basically just because of what is the source of light. That's why lighting is so important. That's why I brought this to your attention, because that was even part of the questions that we were asking yesterday. What do we need to control when we're inferring color? Probably the number one thing that we need to control is the light source. Any deviation of that light source is going to give us problems. Most specifically, if we can control the light source and go beyond just the visible range, we can target other compounds of interest. And I'll mention those later. So as you can see, if these are our receptors, and within this range, it's only 33% of that whole spectrum in color. We could see that regardless of the type of light that we have, this is two different light sources, we will always infer these two different objects of having the same color. So controlling light is very important. How do we describe color now? This is basically the Grothem first law, and we can describe color with three different values. It's three-dimensional. That's basically when we're defining color, we relate it back to what we are inferring. We have three different cones: red, green, and blue. RGB, red, green, and blue. And then we can relate that. We see that in printers, for example. You have three printer inks, and you can generate pretty much any color out there. But when we're describing, or when we're talking about the language of color, it's not that we're describing the color exhaustively. It's that we found a way of relating three values to what we know as color. So we've trained the systems to adjust to our eyes. That's basically the science of color. So in other words, we're mimicking the sensation of the cones in the eye to specific measurements. And this is what forms the fundamental basic of the color language. And it's used till the day of today in all the colorimeters and all the ways of us inferring color. There's different languages of color, and they typically all relate to each other. And these different languages of color were developed for specific applications. For example, in the fruit industry, we use the LAB values, which is typically assessed to assess the color of produce. But there's others, like the hue, Munsell hue, for example, which allows a larger array of different pastel colors, and therefore it gives us more of a natural color notation. Actually, there is some produce industry, they use this hue chroma values to define the color of their product. One of them is the processing peach industry here in California, because they've, and actually it was Professor Carlos Crisoso and David Slaughter who developed this study. They found that LAB wasn't a really good descriptor of all the array of colors that the peach would present them. So they determined that hue chroma values were much more accurate descriptors of color. So again, it's specific to an application when we describe color. And when we're quantifying color, we can use different color matching functions that can either directly relate to what the color matching function of our eye is, or others, like this one, the CIXYZ standard color observer, where the difference between a colorimeter and a spectrophotometer is that the colorimeter measures the sum of all the matching colors within that function, while a spectrophotometer is only measuring a spectrum. So it's a one line information. It's not offering color. It's just one line. And again, look at this value K. Light source normalization factor. Why? Because illumination is very important. And we repeat this color matching function to the red cone, the blue cone, and the green cone to determine color. This is just an example of quantifying color, where this is what we understand as color, but this is the spectrum of this color. So red, for us to look at a red ripe tomato, what light is it reflecting? Blue and green. Exactly. So we have the different chlorophyll levels, where here, green and ripe tomatoes in the bottom, and chlorophyll, higher chlorophyll is in the top. This is the peel reflectance percentage, and this is the different wavelength. And this is actually the human eye cone receptor for sensitivity of red. And you could see that our eyes within that region can differentiate between different maturity levels of this tomato, in this case, or different colors. So again, our eyes, our receptors, and our brain have been trained to differentiate between them. And when we explain color, there's different notations of color. In this case, I'm just showing the relationship. You don't need to memorize these formulas. You can access them later. I'm showing a relationship between what I talked in the X, Y, Z, two different measurements of color. And basically what they did is that they're just trying to offer that crispness, or be able that our human eye can differentiate between one color and the other. Something very important for color is specular reflectance in the product. And this is how we design colorimeters. On a waxy surface, the specular reflectance can mask the color effects of pigments because it's reflecting basically all of the possible colors. It's a very waxy environment, so it reflects light pretty much back. And the specular component is only observed at the symmetric angle of which the light source is. So we have this light source, let's say the sun, any lamp or whatever, and specular reflectance will be reflected at exactly the same angle of which that light source is coming in. So if we measure color within that specular reflection region, we are not measuring color properly. By switching that angle and having an observer at a different location, by eliminating that specular reflection, now we can study color and we could determine color. If we would not eliminate specular reflectance from a colorimeter, this is what we would think is color. While this is the real color of this weed or whatever there is. It's green, nice green or other crisp colors. Here's just reflecting everything. So basically, when you have a colorimeter, and I think that all of us here have used the colorimeter, this is basically how they work. We have a specular excluded, where the observer is, or the appearance of color is strongly affected by gloss in this measurement, because the observer is taking into account that specular reflectance, like here. But if we eliminate this, we can discern color much more accurately. And this is exactly how a colorimeter works. As you can see here, the specimen or the reflected spot is eliminating the specular reflectance, and therefore this does not affect gloss in the measurement, or it's called specular included. There's some applications though, where we do need to study that specular reflectance. And I know you, Marita, you had a gloss meter in your lab. That's the opposite. This is a gloss meter right here. This is a colorimeter. A gloss meter includes that specular reflectance. A colorimeter excludes that specular reflectance. That's how one or the other works. So and in certain instances, we need to measure gloss, waxing, for example, the effects of wax in the appearance and the shininess of the surface of our product. Then we're not interested of color. We're interested only in shininess. And that's when we use what we know as a gloss meter. I've said that we can define color using 3 different numbers. Let's use this as an example. And we have a green tomato and a red tomato right here on the left. If we look at the L value of this green tomato, it's around 68. I have the point right here. That's the lightness, or the difference between the dark or the difference between black and white, sorry. Then we locate A, which is minus 40 around here. A is the difference in the red and green component. And last but not least, we have B around 55, or the difference between the yellow and blue component. And that's how we can locate this green tomato. Same thing for the opposite for the red tomato right here, where it's a different color. So only with these 3 values within this color color theory model, we can differentiate between both. Now we can offer a computer a number. hey, anything within this 29, 42, 27 is a mature, ripe, red tomato, and anything below that is not. And we could start sorting, classifying between one or the other. Computer vision is a tad more complex though, because we have a third dimension or another dimension, which is a spatial dimension and a picture. So we will learn a little bit more in the talk of Roberto of how actually a color sorter works. But in basics, what is happening is that if we take a picture, we can do many things with that picture. We can crop it, we can segment it, we can extract features, and we can even extract color features, the RGB channels, as we can see here. And from those, we can again explain color or determine what is the color of this. Typically what happens is that then we develop a classifier where we could differentiate between different colors or alternatively different properties too. Like in this case, a tip from a middle stem and the bottom stem. What were the features that we measured to differentiate between tip, middle stem, and bottom stem? Is a combination of color and textural features, or the relationship between one pixel to another. That's when having color vision has an advantage. We can add features to it. We don't necessarily need to exclusively rely on one instance of color. And those features can add additional information, integrity, other properties, defects, and so on. That's the importance of the computer vision systems. We've successfully developed computer vision systems to automatically measure color of, for example, walnut kernels. Look at this picture right here. If I could have the ability of zooming in here, this is actually a dome. It's a light dome. We found that if we would have a direct light, like this one, for example, that I have right here, to the walnuts, we were not able to accurately discern the color of walnuts. So we had to basically develop this dome where light is emitted to the object at different angles. And therefore we get a cleaner color estimation. This specific method led to a high throughput phenotyping technique led by Professor Pat Brown, where now they're using this computer vision system and doing all their magic and tying it with developing new varieties that do not lose color. So we're using this as a tool. It's not a sorting tool, but you're using this as a tool that offers breeders a way of assessing and very accurately assessing color. Of course, this needs to be compared and typically calibrated with traditional vision assessment, which is human assessment, how it's done right now. But this is much faster, much high throughput, and much easier to perform, less labor. Typically, what you do is you calibrate it to a known color source. Back in this case, it was an X-ray color chart where we exactly can measure the color of every single block here and relate it to the exact color of the walnut. Now let's talk about, we were talking about here earlier today about hyperspectral and multispectral imaging. And of course, this includes color. Basically, we have a multispectral imaging technique within our eyes and our brain. That's how we work. But a hyperspectral camera can have a higher resolution. And there is commercially available hyperspectral cameras and sorting systems that can go just beyond to what our ability is as humans. The problem is probably the cost and its applicability. But hyperspectral imaging cameras, for example, we can have a camera that could continuously image objects within 367 and 980 nanometers, which is beyond color. And then we start studying the product or the properties of the product even further. But what is the difference between hyperspectral and multispectral? And sorry, before I explain that difference, if you have, even in the near infrared region and in the color region, what would you say is the imaging depth. What is the color penetration? What is the light penetration? The maximum light penetration. As you can remember in the electromagnetic spectrum, near-infrared light has less energy compared to X-ray. So does near-infrared light penetrate more than X-ray? Yes or no? No. But what is the penetration of near-infrared light? Just give a number in millimeters. 1 to 2 millimeters. So if I tell you I can determine a defect 10 millimeters inside an apple using a hyperspectral imager, is that accurate? It's not, because we don't have the potential of doing that. Regardless of all the AI, regardless of what we do, we just do not have the potential of perceiving that difference. And that's deceiving, because one thing that we've experienced is that, and especially, I'm not pointing fingers, but especially many startup companies make us believe that the next big thing is AI and that that's going to solve all our problems regarding of our ability to measure. That's far from the truth. There's only so much we could do with color. I do believe that AI techniques, neural network, can offer additional methods, or it can strengthen our methods. Don't take me wrong, but they're not miracles either, okay? Because we have some restrictions in terms of how much can light penetrate. In many instances, yes, what is going to happen is that the external properties of the fruit are somehow going to slightly change based on those internal properties, and therefore we can detect issues from the outside. But what we have found is that that typically happens in the extreme scenarios, when it's too late. We don't want to sort that anyways. That's the major challenges, especially when we're dealing with optics. So the difference, again, between a multispectral imager, which is, by the way, less expensive than a hyperspectral imager, is that it behaves like our eyes. We have between 3 to 10 bands, broader bands, where we're averaging color, and we can somehow determine properties. But if we want to zoom in specifically, a hyperspectral imager could be a great option, because this is consistent of narrow bands, separations between 10 to 20 nanometers, and you have hundreds of thousands of bands where you can acquire information. But of course, considerations when it comes to developing equipment is not only its ability of inferring this, but also cost. Fancier hyperspectral imaging cameras are significantly more expensive than multispectral cameras or single spectral cameras. Now we can simplify this even further, which is what a lot of inline systems do with the purpose of high throughput, is to study the spectroscopy. So they're not looking at color, but they're looking at a spectrum. And this basically studies the interaction of any light between the sample and what is the spectrum that we're generating. And data is typically represented in the y-axis, it's an intensity, and the x-axis is the wavelength. And depending on what are the constituents, the pigments, and everything, that spectrum changes from one to another. And there's many ways that we could either do this online or using portable sensors, different modalities of doing this. I mean, there's many, but we typically rely on 3 difference. The first is reflectance, where light is emitted. Here, by the way, let me just talk about the components here. D here is the lamp or the light source, whatever it is. B is the sample. Let's assume this is an olive. We were talking about olives this morning. A is just the holder. C is the fiber optic, and E is the multi-waveband light sensor, or the light sensor that interprets how that light reflects from the object. So by this reflectance effect, we can determine what is the color or other constituents. If the product is small enough, like a cherry, or if, of course, if it doesn't have a pit and light can transmit, we can have transmittance measurements too, where we're averaging up all the information within, or interactance, where light is emitted in one direction and it's captured at a completely different direction after it's interacted with the olive in this case. So we can acquire more information regarding properties of that fruit. This is what I meant by identification of wavelengths, especially in the near infrared range or absorbers for different properties. And forgive me for the quality of this. Here, I don't want you to read all of it, but this is very hard to find. This specific table here is very hard to find because it's not, it's not very broadly available, but this was developed in the USDA where they basically explored at every single wavelength and determined what were the components within whatever that would reflect or absorb light. So let's just use one as an example, whichever. Sugars, that's important for properties of sweetness, for example. Look at the wavelengths. Basically anything above 800 nanometers, 838 and above. And the asterisks right here, if we look at the asterisks, indicate relative strength, where 3 asterisks is the strongest bands. So if I tell you, I am using the visible range between 350 to 700 nanometers approximately, and I can tell you exactly what are the sugars in this strawberry. Can I do that? Why can't I do that? Because the sugars are absorbed beyond that. That's why we say that in many instances, color can change in a fruit, but that doesn't necessarily directly relate to the measurements of sugar. And that's why it's not trivial. That's why systems like the ones that we're going to see later today are not necessarily just relying on the vision region. They're looking at beyond that, and it's typically in the near infrared region. Because in the near infrared region, we're exciting many compounds of interest: oil, starch, proteins, water for dry matter content. You mentioned dry matter, for example, that it was important as a measurement of quality, like in what's this, avocados, it is. And we would need to go and try to explore within those different wavelengths what reflects to that dry matter content or water content more accurately. And that's what we know as chemometrics. And I won't go into that, by the way, because I don't want to put you to sleep. But chemometric techniques are just old-fashioned partial linear regression methods where we relate measurements from a spectrum to whatever we want to measure, sugar levels or whatever. It's the predecessor of AI, call it that way. We've been doing this for many, many years, AI included, neural networks. What is the difference between this is that it's not linear. We can, neural networks or artificial intelligence acts like a brain. It's very complex. And in many cases, we can't even explain that complexity. It's just adding neurons to it, and we don't even know where it comes from. But it gives us an output, and it can, relate to constituents. So they are valid, but they're not miracle either. This is just a very nice example of light penetration inside an onion that is used to quantify constituents, pigments, or others. But as you could tell, it just has a certain penetration. It's not transmitting through the whole onion, So we are, to a certain point, just inferring quality around that light. That's why when you develop calibration algorithms to discern sugar levels, for example, in a peach compared with a cherry, which one do you think is going to be more accurate? The cherry or the peach? The cherry, because it's smaller. So it interacts with more of the fruit. Simple as that. Beer's law is related in that dimension. So that's why in every single instance, or in the majority of instances, when you are calibrating small fruits, you look like a champ. But as soon as you move to something that has more diversity inside, it can't penetrate that much. We were talking this morning about a cantaloupe or the melons. That's when you do not look that cool anymore, you know, as an engineer. So it's just physics of color. That's it. We can explain this. Of course, there's different methods or different wavelengths that we could use. And I know that Tomra has I had the pleasure of working with the company that Tomra bought, which was BEST, Belgium Electronic Sorting Technologies. That was one of the first developers of X-ray imaging. And these images were taking in that BEST electronic technology. And this was my PhD, actually, assessing if we could determine quality attributes of chestnut specifically using X-ray. What we found is that, unfortunately, the defects or the density, the changes in density between the defective tissue and that one that is not defective was too close, so we couldn't really discern quality attributes. That doesn't mean that this system is not valid, because there's other applications that I'll show later. But we also explored computer tomography, which is basically a fancy way of saying, I'm taking more than one X-ray image, so I'm gathering more information when I can make informed decisions. This one here is the same as this, and this here is the same as this one, and this one is the same right here. And at that point, using computer tomography, we developed fairly accurate methods, two-dimensional methods of assessing their internal quality of products. This is the dream, by the way, because there's no commercially available computer tomographer that is used for sorting purposes. And the reasoning is throughput. Palmer is going to talk a little bit more about the throughput, but one big thing is that we need to sort around 400 items per second. That's not trivial. But we can't do that with moving parts like an X-ray. But I know that there's some companies, and they're exploring probably not directly a computer tomography, but probably several angles and so on, where we can just start discerning internal quality a little bit better. You want to do AI? Look at this. This is a healthy chestnut. This is a damaged chestnut or a rotten chestnut. Be my AI and tell me where we have rotten chestnuts. All seem kind of healthy to me. Oh, now we go. That's when we start looking at defects. And this is exactly what, you see those? Look at that. That's defective chestnuts. In parallel, I didn't even know at that point what was healthy and what wasn't, by the way. But this X-ray tomographer was just looking at the changes in density, and it was telling us what was healthy and what wasn't. And we could scan this and develop calibration algorithms that would sort this out and tell us which one automatically was decayed and which one was not. Roberto knows this machine because that's what Tomra bought. This was actually in Belgium. I took that picture myself. And we can look at the difference between what is a 2D image and computer tomography images. But again, this is not commercially available. Let's look at other examples. Playing around, I could even build three-dimensional models of chestnuts and turn them around and see where the defective tissue was and where it wasn't. So pretty cool applications. We could differentiate between healthy, partially decayed, completely decayed, and we could also develop spectrums where that was possible and easier to relate to. These are other applications that have been explored. Ron Half, Dr. Ron Half from the USDA in Albany. It's a renowned expert, ex-postdoc of David Slaughter. So we all relate here. You've seen the experts. developed these techniques where he was looking at pineapple translucency using today X-ray imaging, and he developed algorithms to fairly accurately do that. And as you can imagine, detecting insects or insect damage using 2D X-ray should be trivial. Like this here, you can see where the insect burrowed, or whatever we call it, through the olive. Insect damage detection using 2D X-ray imaging. Probably Roberto is willing to share information of how success stories of if they have any, but definitely one big success story with X-ray is foreign matter. Very important for foreign matter detection. This is just a kind of like a picture of the different applications that I've talked this far. I had the pleasure of working with Gerber to assess the fibrous tissue in carrots because it's a choking hazard. If you look at a color image, really at the end of the day, yes, there's some differences between those carrots that do not have any fiber and those that contain different levels of fiber. As we start exploring CT X-ray imaging, there was an evident difference between those that had fiber and those that did not. By the way, bear in mind that this wasn't cut. We didn't cut it was fresh carrots. Here we have already sliced them so we could observe where the fiber was. But the images were acquired in the whole carrot, so we couldn't really tell if there was fiber tissue or not. We found out that later. We also found that using a specific wavelength of 940 nanometers, we could use a near-infrared hyperspectral imager to determine, and this were good classifiers, to differentiate between fibrous and non-fibrous. But we could also simplify this even further using spectroscopy, which is basically a 1x image, or we have intensity in the y-axis, and in the x-axis we have wavelength, where we can see that the spectrum of a non-fibrous carrot is different from that one from a fibrous carrot. So we could sort between them using simple methods, non-invasive methods, by the way. This is just additional readings. If one day you feel like learning more about color, if you haven't learned enough today, two really good sources. Fairly older sources, but the science of color hasn't really changed. So they're not dated at all. Now let's talk a little bit about practical applications. And this is just very brief. Where can we assess quality in practical applications? In the field, during harvest? Is that of interest? Can we do that? I talked about high throughput phenotyping. That's very important for the field. I've worked with breeders here, and we have had little success because the constituents that you're measuring when you're doing high throughput phenotyping are not trivial to measure using non-invasive methods. Carotenoids, for example, carotenoid levels are important for the tomato processing industry. Other measurements that we could relate somehow, but the accuracy of our algorithms wasn't as high to replace chemometric measurements. So, but yeah, we've explored high throughput phenotyping, measurements directly in the field. We'll learn today from Felix what are the type of measurements that they're doing to assess maturity in the field and so on. But then we can apply these different techniques throughout the whole life cycle of a fruit, through pre-sizing, really sizing, or finding the size of a product. We rarely use computer vision system because there are simpler methods, simpler ways of doing this, but it's also a possibility. Hand sorting for external quality, external and internal quality, if we find the proper means of doing it. And still to the day of today, regardless of electronic alternatives to measure color, we always have redundancy, and there's always somebody in the line double checking that everything is going okay. Hopefully, our expectation is that as we strengthen these techniques, as we make them more readily available, less expensive, more robust, then the industry can start applying these techniques for different applications. And of course, it could be applied for processing product too. It doesn't necessarily need to be for the fresh produce industry. So there's different avenues of applying this. And we'll learn about two companies today, as I mentioned. Felix, it's going to show us, their potential from portable instruments, and Roberto's going to talk topics related to inline sorting, which is this component right here mainly. And with that, thank you. I don't know if I have time for questions, or if we have any questions in the chat, or if you have questions, whatever.
I have a question. Can you measure the firmness by measuring the density?
No, unfortunately, firmness, and I didn't talk about firmness, by the way. Thank you for bringing that up. No, I didn't talk about firmness. It's an important attribute. Yes, it is very important attribute, but I was focusing specifically, and that we could do with optical measurements. So firmness is typically a measurement of elasticity. Unfortunately, we could potentially measure bulk density with density measurements, but it doesn't relate to elasticity. So there's alternative methods, and we can talk a whole other section, by the way, of how to measure firmness. If you're interested in exploring or learning that a little bit more, I can help you with that. But I try to focus my talk today in just optical sorting, okay? But so in other words, no, we cannot. There's other methods though.
I have one asking, which is there portable extra device?
Sorry, can you repeat?
Portable extra device you can carry on.
Ironically, yes, there was one developed by, again, David Slaughter. He must think that, but he was in the 1980s. He developed this portable X-ray. You know what? It was his application for weeding purposes, because they could detect the plant. They had this portable X-ray, and they would move it in the field, and they could detect exactly where the plant was, and they would weed anything around it. So it was very accurate, highly accurate, a lot of interest, but it doesn't really, the OSHA people are not really happy with that because of X-rays. So, and Roberto can talk a little bit more about this. When they develop an X-ray sorter, they need to ensure that people are not getting zapped by X-rays. And that was something that we couldn't ensure with those mobile applications. And therefore, they didn't gain tremendous traction because of that. So a little bit of history with that. But yeah, David Slaughter explored those. Mm-hmm.
A question about pomegranates, blackheart and pomegranates. It seems like that one's really hard to detect. Is there research going into the development of machines besides weighing and looking at shape?
Pomegranates are very complex fruit, especially for its quality attributes and what you're measuring. There was some, they were exploring here with MRIs to look at the integrity of the pomegranate. And it was actually studies here in UC Davis. I have some nice pictures that I didn't include. I can show you those, mainly for integrity, for internal defects. And it was well accepted and well developed. MRI is not broadly available in sorting techniques, especially because of its movable parts. But I know of some efforts, and those are proprietary efforts, that they're trying to remove all those moving parts so that you can assess at least internal quality. But I don't know of any well-developed algorithm to detect other properties in pomegranates, for example, sweetness and so on. It's just very tough because of the type of product. Thick skin, and then the structure of of the fruit itself. It's not trivial. Yeah.
So there's just one question from the chat. Maria Fernandez asks, is chlorophyll signal always used for all fruits to predict maturity? If not, what other chemical compounds are frequently used to predict maturity?
Carotenoids is one that I can think of. Beth, anybody else has input regarding that from the biology side of the fruit? Chlorophyll and carotenoids, those are the two that I know. I have some experience, especially with high throughput phenotyping with the tomato industry, and those are the two that they rely on, but I don't know. If
Dry matter would be the other one. I don't know if that's, you're talking about compounds.
color, they're talking about color or maturity.
Those would be the two, I think.
But I mean, if we look at, like, I agree with you, Beth, that maturity could also be measured with dry matter. See my point? So it depends. I mean, if it's directly related to color, then we need to rely on pigments. But if it's not directly related to color, but other like maturity, we have other measurements. Like dry matter is one of them in avocados. I believe kiwi too, or others.
Mango, kiwi.
Yeah.
Potato.
Potatoes. Yeah.
Garlic. I'm
Garlic.
barely learned it here.
There you go. Garlic, potatoes, mango.